Hello everyone. Okay, let's continue the exercise. Exercise 6. Okay, we now proceed to the second sections. The questions which are related to mass transfer. Okay, let's look at question number 9. The composition of moist air is given on the molar basis of 78% of nitrogen gas, 20% of oxygen, and 2% of water vapor. Determine the mass fractions of the constituents of the air. Okay, let's look at the solution. Okay, in question 9. Okay, so the fractions of the constituents of the moist air are given. Okay, so the max fractions of the constituents are to be determined. This is the problem statement. So the purpose of the calculation is to find the mass fraction for molar fraction given in the question. Okay, the small amounts of gases in the air are ignored. The dry air is assumed to consist of nitrogen and oxygen only. Okay, the molar masses of nitrogen, oxygen, and water vapor are 28, 32, 18 kilogram per kilomole respectively. These are the molar masses that you can search from the books, from the handbook. Okay, so or you already know the value from your high school study. Right now, next we have to find the molar masses, molar mass of moist air. Okay, we calculate based on the total molar mass equivalent to the sum of mole fraction times the molar mass of the species I. Okay, so we have nitrogen 28 times the percentage mole fraction 0.78, oxygen 32, the mole fraction is 0.2, and then water, okay, moisture is about 0.02 fraction. Okay, so total we have the total mole fraction of air, moist air is 28.6 kilogram per kilomole. Okay, the mass fraction of constituent gases are determined to be 0.78 times 28 over 28.6. Now we get 0.764. Okay, so it's just the mole fraction converting the mole fraction become mass fraction. So we have to divide by the total mass. Okay, this total mass from this will give us the mass over total mass will give you the fraction by the molar mass. Okay, so now the mass fraction of the nitrogen gas becomes 0.764, which is lower than the mole fraction. Okay, now same thing for oxygen. Okay, it's just 20% of 32 over 28.6. Now it's 0.224, which is 22.4%. Okay, water vapor is 18 over total at 38.6, and the mole fraction given in the question is 0.02. Now we have 0.012 mass fraction, or 0. How much? 1.2%. Okay, so these are the mass fraction, okay, of the moist air. All right. So let's proceed with the question number 10. From a reference, the binary diffusion of DAB of carbon dioxide in air at 200 Kelvin and 1 atmospheric pressure is 0.74 times 10 to the power of negative 5 meters square per second. Determine the binary diffusion coefficient DAB of carbon dioxide in air at two different conditions. The first one is at 400 Kelvin and 0.8 atmospheric pressure. The second one is 600 and 3 atmospheric pressure. Okay, so we can use the this equation by the ratio. Okay, so we have to find from the new DAB, from the old DAB that we have from the reference, based on the temperature and pressure. Remember, the temperature must be in 3/2. Okay, so using this formula, okay, at 400 0.8, but what we have here is at 1 atm and 200 Kelvin. We substitute inside Now we take P2 as our known value, okay, and then P1 will be our new value. Okay, so substitute the value inside, so you're able to get the diffusion of carbon dioxide in air, right? Carbon dioxide in air at 400 Kelvin and 0.8 atmospheric pressure is 3.29 times 10 to the power negative 5 meters square per second. In the second case, at 600 Kelvin and 3 atm, okay, same thing, we assume the first one will be our new value. The old value will be at 400K at 500 Kelvin at 1 atm. Okay, substitute the value inside. We will be able to get the new DAB value, carbon dioxide in air, diffusion coefficient at 600 Kelvin and 3 atm equals to 1.79 times 10 to the negative 5 meters square per second. Alright, so this is quite straightforward. This is a very useful equation for us to predict diffusion coefficient at different temperature and pressure with the reference value. Okay, now helium gas is stored at 293 Kelvin in 3 meter outer diameter spherical container made of 5 centimeter thick pyrex. The molar concentration of helium in the pyrex is 0.0073 kilomole per meter cube at the inner surface and negligible at the outer surface. Okay, so determine the mass flow of helium by diffusion through the pyrex container. Okay, so a sketch of the problem are given here. We have a helium gas in the container at 293 Kelvin. Okay, and then the thickness is 5 centimeter. Okay, the diameter is 3 meter. Okay, 3 meter of the sphere. Okay, and then concentration, the molar concentration inner is at with this 0.73 kilomole per meter cube. This one is in the density, molar density. Okay, so we have a pressurized helium gas in a spherical container. The diffusion rate of the helium gas through the container is to be determined. We want to calculate this. Okay, now we make some assumptions. The mass diffusion is steady state and one dimensional only. In the tank, helium concentration in the sphere through the outer surface practically is 0. Okay, we assume at beginning there is no helium present outside of the sphere container. Okay, and symmetry about the center of the container, so we assume is one dimensional. The diffusions are symmetry. There is no chemical reaction in the pyrex shell, so there is no generation or depletion of helium. So the change of mass is due to diffusion only. There is no reaction or there's no degradation of the helium inside the spherical container. So if you find the binary diffusion coefficient of helium is given as 4.5 times 10 to negative 5 meters square per second. Okay, and molar mass of helium is 4 kilogram per kilomole. Okay, so when I consider total molar concentration to be constant, okay, C equals to Ca plus Cb. Okay, and it's not equals to Cb, equals to constant. Okay, so and Ca plus Cb approximately Cb equals to constant. Okay, and the container be stationary, no diffusion. Okay, and no flux. Okay, this is the flux. There is no diffusion of pyrex molecule, and the concentration of helium in the container is really low, and the molar flow rate of helium through the shell diffusion can be determined from this equation. So this one is n the diffusion of pyrex molecule equals to 0. Okay, NAB, NAB. Sometimes the diffusion rate can be used with n, okay, instead of m. Okay, so it can be NAB equals to 0. So n diffusion of the helium gas through the spherical container can be written in this way. Since the surface area, okay, will be by R Okay, R1, R2, which is the inner diameter and external diameter. Okay, the thickness is actually 0.05 meter, which is the 5 centimeter. Okay, and then the DAB is given here. Okay, and the concentration change is given here. The distance, okay, the distance is at 4 the between the inner surface and external surface. Okay, so our mass fraction will be the mass transfer rate will be 1.8 times 10 to the power negative 15 kilomole per second. Okay, the mass flow rate is determined by molar flow rate. Okay, sorry, this is a molar flow rate, sorry, and we want to get mass one. So we have to multiply the mass the molar flow rate with the molar mass of helium. So we know molar mass of helium is 4 kg per kilomole. So multiply, we get 7.2 times 10 to the negative 15 kg per second. So we keep in the container shell, and the different range of this, you'll take 0.02 year, 0.0023 gram per year. Okay, so the amount of helium leaked out from the container is very small per year, very small amount. So the pyrex is a good container to contain the helium. Very small amount can be diffused out from the container. Okay. Okay, next. Okay, so next, a thin plastic membrane separate the hydrogen from air. Okay, the molar concentration of hydrogen in the membrane at the inner outer surface are determined to be 0.065 and 0.03 kilomole per meter cube respectively. Okay, so the binary diffusion coefficient of hydrogen in plastic and the operation temperature is 5.3 times 10 to the power negative 10 meters square per second. Determine the mass flow rate of hydrogen by diffusion through the membrane under steady state condition if the mass flow rate by hydrogen diffusion through the membrane under steady condition if the thickness of the membrane is 2 millimeter and 0.5 millimeter. Okay, so a thin plastic membrane separate hydrogen from air. So the diffusion rate of hydrogen by diffusion through the membrane under steady condition to be calculated. So mass diffusion is steady and one-dimensional. Hydrogen constant both sides are maintained constant. Symmetry about the center. So you assume the diffusion is happening at symmetry dimension. There is no chemical reaction. There is no generation or depletion of hydrogen in the container. So the binary diffusion coefficient of hydrogen in plastic membrane given as 5.3 times 10 to the power negative 10 meters square per second. Molar mass of hydrogen we know is 2 kg per kilomole. Okay, we can consider total molar concentration to be constant. Our C equals to CA plus CB, approximately CB equal to constant, because we know the other side, the CA is actually 0. There is no concentration at the beginning outside of the membrane. Okay, so there is no diffusion of plastic molecule. So NB equals to 0. The plastic is not diffusing. So the concentration of hydrogen in the membrane is extremely low. CA is nearly 0. In the membrane at the beginning, okay, there will be no hydrogen inside the membrane. Okay, so Ca approximately 0. So that's why our C equals to Cb total. So the molar flow rate of hydrogen through the membrane diffusion per area is determined from molar flux. Can determine from the mole diffusion rate over surface area equals to DAB CA1 CA2 over length, the thickness, which is the travel distance. Okay, so in this case we have the DAB value, the diffusion coefficient value, okay, which is 5.3 times 10 to the power negative 10 meters square per second. The concentration different over the thickness, we will get 1.64 times 10 to the power negative 8 kilomole per meter square second. The mass flow rate is determined by multiplying the molar flow rate by the molar mass of hydrogen. Okay, so it's actually mass flow rate the molar mass times the mole flow rate. So we get 3.29 times 10 to the power negative 10 kilogram per meter square second. Okay, now repeating the calculation for a thick membrane will give you the what is this? This is a molar flux. Okay, molar flux again. Okay, because a cap on top is for molar. Okay, we get DAB delta C over T. Okay, in second case we have 0.5. Uh, just now is how much? 2. 0. 2 mm, sorry. This one is 0.5 mm. Okay, substitute inside here. Now you can see you get a higher molar flux. Okay, when it's the thickness is lower. Okay, so we can convert the molar flux to mass flux by multiplying the uh, molar mass. So we can determine by multiplying and by the area. Okay, membrane area. So if you times the membrane area, if you times the membrane surface area, we are able to get the mass diffusion rate. Okay, or molar diffusion rate. Okay, by times the area. Okay, we can know by times the meter square. Same thing here with the meter square, we can find our diffusion rate. Okay, now we have the last question. A large tank containing ammonia at 1 atmospheric pressure and 25 degrees Celsius vented to the atmosphere through a 3-meter long tube whose internal diameter is 1 centimeter. Determine the rate of loss of ammonia and the rate of infiltration of air into the tank. Okay, so we want to know the ammonia gas diffused out from the container and also the air diffused into the container. Okay, so in this case, a large ammonia tank is vented to the atmosphere. The rate of loss of ammonia and rate of air in infiltration into the tank are to be determined. I'm going to calculate the rate here. The rate of ammonia diffusion rate and also air diffusion rate. Okay, ammonia vapor and atmospheric air are ideal gases, we assume. So we can use the ideal gas equation. The amount of air dissolved in liquid ammonia is negligible, so we don't consider any loss of the air due to solubilization of air in ammonia. Heat is transferred to the ammonia from the surrounding to make up the latent heat of vaporization, and the temperature of ammonia remain constant at 25 degrees Celsius. So the property of ammonia, molar mass, we get 17 kg per kilomole. The molar mass of air is 29 kg per kilomole. Diffusion coefficient of ammonia in air, we can get for 1 atm 35 degrees Celsius as 7.2 times 10 to negative 5 meter square second. So we do the analysis. It's a typical equimolar counter diffusion process. Since the problem involved since the problem involved two reservoir or ideal gas mixture connected to each other by a channel, and the concentration of species in each reservoir, the tank atmosphere remain constant. The flow area, okay, cross-sectional area of the tube, we take the tube as the area. So we take the the diameter here as 1 centimeter. Okay, tube is 3 meter long. Okay, get this, so 1 centimeter. All right, then note that the pressure of ammonia is 1 atm or equals to 101.325 actually, kilopascal. At the bottom of the tube is x equals to 0, and 0 at the top, x equals to L. The molar flow rate is determined from the mass flow rate, mass diffusion rate. Molar diffusion rate. Okay, so the molar flow rate is determined from here after we rearrange the equation here. Okay, so we find the molar diffusion rate by substituting all the DAB value, surface area, pressure different, partial pressure actually, the rate constant, the gas constant, okay, the gas constant times the temperature, 3. This is ideal gas equation. We assume it's ideal gas. So we can use this to substitute and we get the molar flow rate or molar diffusion rate, okay, equals to 2.78 times 10 to negative 11. Okay, so the mass flow rate we just multiply with the molar mass. Now we get 4.73 times 10 to the power negative 10 kg per second, which is about 0.0149 kg per year. It's very small amount. Okay, note that NB equals to negative A because it's equal molar counter diffusion. So they have equal amount of ammonia escape to the atmospheric, and then the equal amount of air replacing the ammonia. Therefore, the molar flow rate of air in the ammonia tank is equal to the molar flow rate of ammonia out of the tank. So the mass flow rate of air into the pipeline become the mole. We take the mole and then times the mass flow rate. We get negative 8.06 times 10 to negative 10 kg per second. So we have answered the questions and we have solved all the problem on mass transfer. So these are basics questions that you should practice and understand. They are equally important, okay, in a final exam. All right, so we are done with the exercise. Okay, so next I would like to continue the recording of this video with some revision. Okay, so let's recap back what we have learned in the whole semester. Okay, so what is important the whole semester that we have learned? We start the course with thermodynamics, some basics of heat transfer and mass transfer. Okay, now if you recall back, thermodynamics term, okay, it comes from two words. Thermo means heat, dynamic means motion. We are studying the motion of heat, right? We also learn about this, the thermodynamic system. The thermodynamics consists of a boundary and surrounding. The boundary actually separates the system with the surrounding, separating the system from surrounding. Okay, now we also learned that there are generally three kind of thermodynamic system. In open system, actually the system allow exchange of energy and exchange of metals. So where you have heat transfer and mass transfer happening. So this kind of system we call it open system. In a closed system, the system only allow the change of energy, so heat transfer can happen, but there is no change of metals. There is no mass transfer. Okay, the third system is an isolated system where the system doesn't allow any change of heat or energy and also mass. So it's a closed isolated system. So totally nothing will change in the system. Okay. We also learn what is enthalpy, what is entropy. Enthalpy usually is denoted by a H, refer to the measure of total heat content in the thermodynamic system under constant pressure. This is the amount of energy contained by any substance at any temperature and pressure. Okay, entropy is usually denoted by S, refer to the measure of level of disorder in the thermodynamic system. How disorder is the molecule or metals. Okay, if in the metals is in gas phase, okay, so it has a high S. So you can see the figure below here. Entropy increase for gas molecule because they are highly in disorder. When it's in solid, the entropy is small, but the enthalpy is in the other way around. In solid, okay, the enthalpy is high because they are closely together. So you need very high enthalpy to make change to them, okay, as compared to gas. Okay, so entropy and enthalpy, they are actually opposite trend. Okay, now we also learn about state of variables. The three main state variables, which are pressure, volume, and temperature. So in a closed system, okay, so when we have a piston, okay, compress, okay, so if it's an ideal gas, Okay, we can describe the change of pressure and volume with the temperature with using of gas constant. Okay, so this equation actually can correlate the state variable. Okay, the pressure, volume, and temperature. They are interchangeable. The effects of all these can be described by this equation. If it's an ideal gas, okay, which is at low pressure, has quite atmospheric pressure, near to atmospheric pressure, not too high, not too low. Okay, and if a real gas that they have a behavior of deviating from ideal gas case or perfect gas case, we have to use a Van der Waals equation using this, where we have to find the value of A and B. Okay, and then we learn about thermodynamic laws. Okay, we have zero law, first law, and second law. Okay, based on zero law, the temperature, the two system equilibrium with the third one are in the thermal equilibrium with each other. So the two system will only equilibrium when the temperature with the third one also reach same value. That means say equilibrium has been achieved. First law, conservation of energy. Okay, energy can change form, but it's neither created nor destroyed. Okay, so first law of thermodynamics tells us the energy balance is always in the amount we supply is equal to the amount that disappear from the system. So it's a conservation of energy. Okay. Second law tells us about entropy of an isolated system always increases. So uh, the energy only transfer from the hot side to the cold side. Okay, and the energy required to move a motor or any engine is always greater than the amount needed because there are losses in the process. Okay, so second law tells us it's only happen from the high energy area to the low energy area, entropy, high entropy to the low entropy. Okay, that's how heat flow through. Okay, and then we learn the basic modes of heat transfer. Okay, if you look at the figure on the top, left side top, okay, we learn about conduction. Okay, energy transfer between adjacent molecules. Convection, okay, the conduction plus motion of fluid. Okay, something like the energy move inside boiling water, the movement of the water molecule, water bubbles. And then the third one is radiation. Radiation is a heat. Radiation happens with the emissions of electromagnetic wave, which the energy can be transferred without a medium. It can happen in a vacuum condition. Okay, now we focus on the conduction first. Okay, when you have a system like this in the figure in the center here, when we heat up a rod, metal rod, the hot atoms will transfer the heat to the surrounding particles. Okay, the collision of particle actually um, move or also transfer the heat to the particle is neighboring particles. Okay, so for, as the time pass by, the heat from one end will transfer to another end. Okay, so this kind of heat transfer mechanism we call it as conduction. Okay, so always the flow of heat is from high temperature side to the low temperature side. Okay, the heat conduction can be described by Fourier law using Q equals to negative Ka delta T delta X. Okay, the K value here is the constant here is called as thermal conductivity. Okay, it can be measured if you have a setup that can measure the length and temperature difference between two sides with the known amount of heat supply to the metals or any conductive material. Okay, then we learn a few terms that required in a heat transfer. The thermal diffusivity, okay, is actually heat conducted per heat stored. Okay, it's actually a ratio of the thermal conductivity over density times the heat capacity. Okay, so thermal diffusivity usually is given in a symbol, is described or denoted by a alpha symbol. Okay, heat capacity, our CP, is actually amount of energy, heat per mass change of temperature. Okay, so we know to change a certain amount, for example, one kg of material, for 1 Celsius, how much energy required. So from this heat capacity, we know for certain weight, for example 1 kg 1 kg of water and 1 kg of gold. Okay, how much energy required to raise 1 degree Celsius? So this value is very important for us to calculate the heat load of a system. Yeah, the CP is important. Then we learn about convection heat transfer. Okay, so you remember convection heat transfer essentially is a conduction heat transfer plus fluid motion. Okay, if the fluid motion without any external force, we call it natural convection. It's driven by the temperature difference and buoyancy and density of the fluid inside the system. By itself, the heat is moved due to the motion of the fluid by nature. Okay, but if you use the external force like a pump, like a stirrer, like a motor, then it's called forced convection. This convective or convection heat transfer, we can describe this, calculate this using a Newton law of cooling, where the heat transfer rate is equals to the HA delta T. A here is the surface area. H here is actually convection heat transfer coefficient. Right? Then we proceed. Now we continue with radiation heat transfer. Okay, there are two kinds of body, black body and gray body. Okay, black body is ideal case where the black body can absorb most of the incident radiant energy and reflect some minor portion, and it also can emit most of the energy supply to the black body, emit that it has in the black body, and retain very small portion, a very ideal case. For gray body, okay, only a small portion can be absorbed by the body, big portion will be reflected by the gray body, or the black body itself can emit some amount of energy but retain quite a large number inside the gray body. Okay, in general, okay, the energy balance, the incidence radiant energy emitted to a surface, okay, so a portion will be absorbed, okay, by a portion described by absorptibility. The alpha here is absorptibility, the fraction absorbed by the material, and also we have 1 minus absorptibility, which is the reflectivity, the amount reflected by the surface. Okay, so we can use Stanford-Boltzmann law to describe the energy emitted by the body. Okay, so we can use the epsilon here, theta, surface area, surface of temperature to the power of 4. Okay, emissivity is described by the epsilon symbol. The alpha, the theta here, sorry, is the Stanford-Boltzmann constant. Okay, remember the temperature, surface temperature must be in Kelvin. Okay, we can calculate the energy emitted by the body. The radiant energy is between, if you see the figure shows here, in a system always the material will release the energy, the radiant energy to the surrounding. At the same time, the surrounding also emitting energy and being absorbed by the solid. So we have to minus the amount emitted by the solid, which is a surface temperature, and the amount absorbed. Okay, we have to minus so that we can get the net radiant energy emitted by a solid. So again, we need the emissivity value, the Stanford-Boltzmann constant, surface area, just the difference between the surface temperature and the surrounding temperature. We just minus, we will get our radiant energy. Okay, now phase transition. Okay, we also learned that heat transfer, or when heat transfer not only at the same state, but as the material absorb heat, evaporation happen, right? So phase change, for example, from water, the liquid water will evaporate, become water vapor, become gas. So as we subsequently increase the temperature and supply more heat, boiling happens. Okay, we can see gas bubble inside the solution. Okay, we get more vapor produced by the boiling process. Okay, and then condensation is actually opposite of the evaporation and boiling process. We have a cold plate on top, maybe. Okay, so the hot vapor evaporated from water liquid, when it's cooled down by the cold metal plate here, maybe it will condense back to the bulk liquid here. Okay, now heat transfer coefficient, the vertical plate, okay, the condensed droplets will then form a layer, a layer, okay, on the surface, okay, on the vertical surface. Okay, so we learn this also. Okay, there are two types of condensation. Okay, the most common case are film condensation. A layer of film can be formed on a flat, vertical flat surface. Okay, but at beginning maybe, yeah, dropwise condensation happens. You can see droplets forming on cold glass. Okay, but as time pass, more and more droplets form. They start to collide and form a film layer. Okay, so the film layer here can be described by this and shown in the figure here. At beginning, it's a laminar flow. It start to flow, right? And we have a very thick film now. The liquid is still flowing on top of the cold wall, cold glass or window. Okay, at beginning it's actually in the laminar flow. Slowly you get a wavy laminar, and then above 1800 Reynolds number, we can describe by this Reynolds number, it become a turbulent. Right? So the Reynolds number case here, we can use the formula here. Okay, you check back the lecture notes to calculate the Reynolds number for condensation film. Okay, condensed film on a cold wall, cold glass. Okay, and then we need a Pladdle number or Nusselt number to determine the correlation, to determine the heat transfer coefficient. Okay, now there are two general one that we can use, short general equation, for heat transfer coefficient of the condensate on a vertical plate. We can use this equation to get the H value, and you can use another one here when we are considering the condensation happens on a horizontal tube at the curved surface. We can use the second equation here, right? Then we also actually, before the condensation, we cover on boiling first. We learn boiling. Okay, there are three types of boiling classification, right? So the first one is just Newick boiling, or first actually convection boiling, then Newick boiling, then we have film boiling. Okay, in between of Newick boiling and film boiling, we call it a transition phase, transition boiling. Okay, so if you check the boiling curve, okay, so the boiling, you can see y-axis is the heat supply, x-axis is the change of temperature between the temperature of the uh, heated surface, and the Ts is saturated temperature, which is the boiling point. The boiling point. Okay, so as we keep on supplying heat, temperature change increase. Okay, until point A is still at the very single phase convection boiling, which no gas bubble is formed. Okay, as we proceed further, more heat is supplied until point B. Okay, point B is actually very important. It's called maximum heat flux point or critical heat flux point here. Okay, so at the the boiling between point A and point B, you can separate them into two phases. The first phase, isolated bubbles are formed. So, but the bubble actually form, and then you usually not reach to the surface of the liquid, because they will condense back and come back to the liquid again. Okay, after this second point, you get a lot of large bubble to the second phase of Newick boiling. Okay, after point B, you get a lot of bubbles. They start to boil, and then you can see a drop in the boiling energy. Heat is dropped. Okay, because a lot of gas bubble form on top of the heated surface, and they are become a barrier, stopping the heat transfer. Okay, so the heat transfer rate will drop to the point C, or you call it a latent force point. Okay, after the latent force point, you can see an increase in heat transfer rate again, because the air bubbles start to break. Okay, so the layer, the resistant layer on top of the heat transfer surface is break now. So the heat transfer rate will increase back until point D. Okay, after point D, the heat transfer rate will be very high. But this point will also a dangerous point because it's at very high temperature now. The point D is at very high temperature. Normally is above the melting point of metal. So your device may be destroyed if you hit beyond point D. Okay, so our interest is always at Nulic boiling area. Okay, when we design our equipment, okay, we should have a good boiling condition. All right. So the Nulic boiling area, you can use this correlation. We call it Rowe-Sinows correlation. Okay, use this correlation, right, as a general in Nulic boiling. But more specifically, if you heated surface at a flat plate, we can use the first correlation. For a vertical plate, we use the second equation. Okay, so at the boil peak, at the maximum heat flux, we use this equation. Heat transfer rate is equal to this. All right. At the flame boiling region, we can use the one at the right hand side, and usually at this region it also involve radiation heat transfer. Okay, not only convective but radiation. We can find the heat transfer coefficient based on convection and also radiation. Okay, so the convection heat transfer coefficient we calculate with the first equation. The radiation heat transfer coefficient we calculate with the second equation. We substitute the value inside here, and then we get the total convective heat transfer coefficient. All right. Then we learn another sections on thermal resistance. We use the thermal resistance concept. Okay, remember for conduction we can calculate the conduction heat transfer resistance. It's L over Ka. Convection heat transfer coefficient 1 over HA, okay, and radiation heat transfer 1 over H surface area. Okay, now if you see the figure here, we have a flow of motion of liquid here passing through a wall of 2 layers and then another fluid outside of the wall. Okay, so if you have a flow of fluid here is a convective, right? Convection heat transfer. Okay, so we have a convection radiation thermal resistance here. Then we have 2 layers of wall. Here is conduction resistance. Okay, first layer, and then conduction resistance second layer, and then outside of this we have a convection, okay, or convective thermal resistance here. So we can see here we have a convective or convection resistance, conduction resistance, and then outside of here, if it's only convection, then we have another resistance here. But if this area involve radiation, we can have parallel another radiation of another thermal resistance due to radiation. So now we have a parallel because two types of heat transfer happen here. Okay, we have two thermal resistance here. Okay, so we can write the equation like this. Once we find the total resistance, total thermal resistance, we can calculate the overall heat transfer coefficient. On the right hand side here now, we are talking about overall heat transfer coefficient, overall heat transfer rate. We have to find the overall heat transfer coefficient, which we need the R total, the total resistance from the thermal resistance circuit. Okay, so once we have UA here, we substitute inside and then multiply with the delta T, we will get our total Q. Okay, now we focus on a curve or a double pipe system because most of the heat transfer happen with the double pipe. So when it involve a curved surface or a cylinder type, the conductive thermal resistance is in the ratio of the outer diameter to the inner diameter over 2 pi K L. This is for cylinder. Okay, so in this case, if it's a double pipe, okay, we have a fluid inside, a curved cylinder wall here, and another fluid outside. So we can consider the total resistance, total thermal resistance at this. So inner fluid by convection, okay, is 1 over convective or convection heat transfer coefficient times the inner surface area, and the wall resistance, okay, the conduction wall resistance, and outer surface here we have another resistance with convection resistance, okay, 1 over H not HA, okay, based on outer surface area. Okay, then we talk about heat exchanger. Okay, there are two general many types of classification system. We use this one non-contact and contact type. Okay, under contact type, we learn a few: scripted surface, shell and tube, tubular, and plate. The contact type, steam injection and steam infusion. Okay, in general, heat exchanger, we can calculate the heat load by MC delta T based on inlet and outlet temperature, okay, of the heat exchanger. And then the overall heat transfer coefficient is usually based on the convection inside, thermal conduction by the heat exchanger wall, and then another convection outside, because involve two fluid for heat exchange. And we have to consider the fouling factors. Okay, if it's happening at outside, you add here. It depends, you can be inside, outside, but we have to add the fouling factors. Okay, there are a few types of heat exchanger we discussed in the lecture. Okay, we have plate heat exchanger, shell and tube heat exchanger, tubular heat exchanger, scripted surface heat exchanger, and direct steam or injection or infusion. Okay, so few example here. Sorry, I think I've already changed, but these are a few example for food application. Okay, so some advantages. Okay, so we know that plate heat exchangers, very high efficiency, very compact, easy to clean, small footprint. That means you require very small surface area to install the plate heat exchanger. Okay, but the problem here is not good for high viscous fluid. Okay, shell and tube heat exchanger is good to handle slightly high pressure and temperature, suitable for viscous and particulate fluid. Very durable, very long lifespan, but moderate efficiency, not so efficient, and you require large footprints. You need a big space to install this, and it's sometimes quite difficult to clean. Okay, tubular heat exchanger, good for viscous fluid, can handle particular fluid. Okay, and hygiene design available, but this one expensive, high cost, and large footprint, need a large area too. Cleaning can be challenging if the fluid is very viscous. Okay, scripted surface is very good for fouling type of fluid. Okay, very viscous, very sticky products can use this scripted surface heat exchanger. Okay, maintain uniform heating because you have a scripted, right, a moving impeller inside the heat exchanger. Very expensive, high energy consumption because it's a very complex design. Okay, last one is the direct injection or infusion heater. Very fast heating, required but it reduces thermal damage because very fast temperature and very short time. Okay, so you can retain all the properties of the material. Okay, but the problem is you must provide very good quality steam, must very clean steam. If not, the steam may contaminate the product because the steam is directly in contact with the product. Okay, and then we talk about shell and tube heat exchanger, for example. So shell and tube heat exchanger is very common use in industry because it has high heat transfer area per volume, can handle high pressure and temperature on both sides, the utility side and also the process side. Okay, and flexible design, easy to maintain and clean, suitable for dirty and fouling fluid, allow heat expansion, robust and durable, very long service life. Can accommodate for phase change. If you have evaporation happen or condensation happen, it can, it has no problem. Okay, there are two general arrangement of the flow inside the shell and tube heat exchanger or tubular heat exchanger. The simplest design of shell and tube heat exchanger is actually a two pipe double pipe heat exchanger. Okay, you can have a parallel flow, the inlet hot and cold inlet at the same side. So in this case, hot and cold fluid at inlet is at the left side, and cold and hot fluid outlet is at the right side. Okay, this is called parallel flow or co-current flow. Counter flow is for fluid, both fluid at the different moving at different direction. Okay, the hot fluid is from left to right from this case, and cold fluid is from right to the left. And this case, you can see the profile, the temperature and distance profile. Parallel flow, concurrent flow, you can see the delta T is large at the inlet and slowly reduce towards the outlet. But counter flow has a more uniform delta T along the distance inside the heat exchanger. Okay, fouling factor. Okay, the overall transfer coefficient of the dirty fluid and clean fluid, the difference is very small. We have to find the difference of these to get the fouling factors. Okay, now you need to be careful The fouling factor, the fouling can happen on the outer surface of the inner tube and also can happen in inner surface of the tube. Okay, if like this case, inner and outer surface of the tube has fouling happening, deposition of fouling on the surfaces, inner and outer surface, we have to consider the fouling factors for inner and outer. Then you must add extra thermal resistance here. Okay, then we also learn two ways to calculate heat exchangers analysis. The first case is log mean temperature difference. We have to calculate the delta T1 at the inlet and delta T2 at the outlet. Natural log of delta T1 over delta T2, calculate the log mean temperature difference and substitute the log mean temperature difference to get the Q, the total Q of the heat exchanger. Okay, so this is log mean temperature difference, and we can use the effective NTU methods. We have to calculate the lower heat capacity rate for cold fluid and hot fluid. Among these two, the minimum we select to find the Qmax. From the Qmax, we can find the efficiency, and also from the C mean, we can find our NTU, the effective temperature unit. Okay, and also the ratio of the C to get the correlation, the right correlation to find the effectiveness and also the NTU value. Okay, so usually we use log mean temperature when we have the temperatures at the inlet and outlet. Okay, when we don't have the outlet temperature, for example, it's more convenient to use effective NTU method. Okay, then we learn mass transfer. We know the definition of diffusions. Diffusion happens only when we have a concentration gradient. The molecule or substance, particles will move from higher concentration area to the lower concentration area. Okay, it's a passive process where no energy needed to move, okay, of the particle from high concentration to low concentration. Okay, we can describe the diffusion process by using this concentration distance profile, just like the heat exchanger. We have the concentration, so we need to show the concentration gradient here. Okay, at 2 point, at Z1 is a 0.1 and Z2 is 0.2. When we have concentration high at Z1, 0.1, and low concentration of the substance at 0.2, Z2, the flux is positive because the concentration gradient is positive, is negative. That means moving from high concentration to low concentration. Our Ca2 minus Ca1 is in negative value, so we get a positive flux. We can calculate not only by concentration, we can use the partial pressure by using partial pressure. Okay, now the diffusion process can be described by Fick's law. We learn about first law and second law. Okay, so the first law tells us the change of concentration over distance. Okay, and the heat flux is actually in terms of this molar flux. Okay, in terms of per area. Okay, kilomole of A per meter square. Okay, and the change, we want to know the change of concentration at a point, then we have to use second law of Fick's law, Fick's second law, to determine the change of concentration at every point over time. Now you can see the plot here. At point x1, the change of the concentration over time. Okay, the gradient. So we can find from second law of Fick's law. Okay, so it's del Ca over del T equals to dAb del 2Ca and over del x squared. Okay, but second law is not covered in the lecture. Okay, we only focus on the first law, Fick's first law. Okay, then we learn from Fick's first law how we calculate the mass transfer rate. So we can calculate the rate of mass diffusion. Okay, this amount you can in terms of mass flow rate, mass diffusion rate or molar diffusion rate. Okay, is dAba del Ca over del x. Okay, and mass rate of mass convection. Okay, if you want to know the balance, the mass balance, so always the convection part involved in the mass transfer, right? So the mass convection is equal to H, the convection heat transfer coefficient times the surface area times the concentration gradient, equals to the rate of mass diffusion. Okay, and in the calculation of mass diffusion, we need diffusion coefficient or diffusivity, mass diffusivity. Okay, diffusivity can determine from handbooks, from tables, or from correlation actually. So if you know the diffusivity or diffusion coefficient at one temperature and pressure, we can predict it at a different temperature and pressure. Okay, we can use this prediction equation, okay, from the known temperature and pressure to determine the one that we don't know. Okay, so there are a few things that we have to bear in mind. Okay, for mass and molar fraction, we can use this general correlation. Can interchange this value to determine the concentration that we need in our mass. The diffusion can be in a mass diffusion or molar diffusion. Okay, and also it can be uh, determined by the partial pressure and total pressure, and also the mole and total mole to get the mole fraction. Okay, so we can calculate the mole fraction to determine the partial pressure. Okay, we can substitute the concentration by partial pressure for ideal gas. Okay, and since water vapor air are very useful, this system, so we can use this well-developed equation for vapor in air to determine the diffusion coefficient of vapor in air using this equation 1.87 times 10 to the power negative 10 T to the power 2.072 over P. This is a very useful correlation to determine the diffusion coefficient of water vapor in air. Okay, so these are all important equation for mass transfer. Okay, so if to understand more, you can refer back to the lecture note. This is a quick revision. Okay, so if you understand all I mentioned here, that means you have mastered the subject of this semester. Okay, thank you for listening. Thank you for taking this course. Glad to share my experience. Okay, if you have a question, you can feel free to ask. Okay, generally, if you understand everything I mentioned here, I'm sure you can score well with final exam with flying colors. Okay, all the best to your studies and all the best for your final exam. Good luck, everyone. Okay, thank you very much again, and I see you when I see you. Okay, bye. Bye bye.